that's where I've been spending the majority of my time in research, trying to understand about what it is. No background in polyurethane really, just chemistry, and trial and error again and again and again and again, and eventually you get somewhere. You meet people, you talk things, you get new ideas, you test, it fails, you test, you keep going, and eventually things start to happen. A lot of the machinery that we have is all unique. You can't, it's all been either bought as a basic module and then modified, or we make it all ourselves. Most of the machines we have are made, maybe some software is not made ourselves, but most of the machines we have in-house, all the grinding machines we have are made. I mean, this is a unique industry. There's no real background to what we've all started in. On the right-hand side of the picture, there's a polyester point machine. It's a big screw, hardened metal screw, and into the top of this screw is injected resin and sand, and it mixes it, and there's a little white vacuum chamber halfway through, so the material is vacuumed. The left-hand picture is what I'm going to be talking about most during this talk. It's how I understand, or try to understand, how well polyurethane wears down. It's been the key question for the last, I don't know, 10 years. Everyone's been wanting a polyurethane that lasts longer. Many different things have been done, but until you really know what's happening, it's really difficult to wait for the wall to give you an answer, and it's a very subjective answer. Often people make a shape and categorize it and modify the shape slightly with the style to make it look different, give it a theme, different shapes and sizes. By the way, we really only deal with the small end of the spectrum. Composite X is all about casting. We don't make from, let's say, 60 centimeters, 70 centimeters and above. This is not where we specialize. We're not going to go into this. A lot over time, often exposed to UV light, polyurethane especially sensitive, MDI systems. You have to put a lot of effort into stabilize them. Strength. Yeah, there's another guy behind. This is our mold manager, Newsent, and behind him is our technical manager, Nancy. Together they make up 260 kilos. Strength, what does it mean? These are some of the methods we used for testing. There's an impact testing machine for measuring, which is very equivalent to dropping a hole in the floor. And this is a very old machine that me and Lloyd made back in the day. I used to enjoy giving Lloyd different bars to test and not really telling him how strong it was, because when this thing breaks, it makes a big bang in it. Texture. This is the main one, and I'll talk more about this a bit later on. So how does the texture come about? The climb and hold, I'm guessing people want it to feel like rock. What they used to climb, or what they climbed on, what they used to remember what they climbed on. Of course, it doesn't have to feel like rock. It can be smooth, it can be very rough, it can hurt, it can not hurt, it can feel soft or very sharp. And the designers of the holes in production, we need to modify it. Sometimes we put some dual texture parts in it. So analysing this foam is very important. How can foam affect textures? Bubble size of the foam, some bigger bubbles, coarser products. But more important than the foam size is the finishing you use. So sandpaper. So what you put on the end of it. The difference between a 2000 grit sandpaper and a 60 grit sandpaper is massive. This is the old machine we used to use for testing. This testing machine that I'll show you a bit later is the fourth generation. This original idea, I put rubber on the outside, but the rubber wears down too fast, and you have to change it. So another parameter, weight. Perceived weight. Root setters want lightweight holes. The whole hold needs to be light, as opposed to focusing on the density of the material. So originally I thought we put in well, we had the British bolt system was mostly countersunk bolts, and in Europe people use mostly cathode bolts. So what I thought is, let's make the profile that you can fit both the countersunk and the cathode bolt together. And that's it. You can fit a countersunk bolt and a cap in without absolutely no need for these washers. Just the dual butt washer is only important for polyester. Polyurethane doesn't make any difference at all. In our industry, we're the first people to start using autoclaves, and we still are today. I won't stop. It's a good way of guaranteeing surface finish and quality. So how does an autoclave work? On the top here you have a mould. Let's imagine this is completely silicon underneath, and this is how it looks when you focus on it. If you pour resin into the mould without using an autoclave is just a pressure chamber. The resin doesn't go all the way down to the end of your needles. It doesn't fill all the gaps of the mould. But, and this again was completely out of the blue. I'll tell you what happened in a minute. When you put the pressure on it, the air that's in that gap goes into the silicon, because silicon is porous. And the vacuum the space that's created from pushing them down from above, it forces the resin into the gap. So you're left with a perfect copy. Every single product that we make goes through this process. How did I find this? Again, by accident. It completely. I never expected an autoclave to make a great quality finish. I was experimenting with polyurethane in the early days by making foam. I was thinking, well, let's make a foam hold. So let's take a polyurethane which is during the foaming process, pour it in the mold, then chap it. And what I did, I put it in the autoclave pressure chamber to control the height of the foam. Because foam just goes up to its own height, and it's very difficult to predict when you pour it in the mold where it's going to get to. So I was using pressure to control the height, and I got this. And then I looked at the surface and thought, oh, this is really good. It's a different, it's a better finish. So then that made the connection for the future that autoclaves can force resin in all places in the mold and give a better finish and help reduce two different properties of two different polyrethane. Very laborious process, coating the mold. And that's one of the reasons I discontinued it. It's also a little bit difficult to control in the production process. A year later, we made Dynolite, which is still going today. Dynolite is the cheaper end of the polyurethane that we do. Cheap MDI system, which is semi-regenerative. I don't think it's as good as Aragon system, but the idea is the same behind it. That the initial texture isn't there. It's not designed to be hard wearing as such, but it's designed to give a texture over time. Okay, texture. So how does the hold wear down? If we're considering foam-based shapes, foam holds, the surface of the hold looks like this, cutaway bubbles. And then when you rub it with your feet, and by the way, if there's any doubt of the main reason that holds wear down, it is because of the climbing shoe. It's not by chalk, it's not by hands, it is mechanical wear by climbing rubber shoe. And when you analyze, look under a microscope at what's being done after a wear, there are two different ways that the material can become polished as such. One is that the needles are completely taken away. The other is that the needles can fall down flat and in the same way give a polished surface. One of them, the second one, doesn't have any mass change, so the hold stays the same. There's no change in the weight. For the first method of wear, there's a significant change in weight. So, to generate this test, I made a machine, and the machine is a piece of rubber. It's Vibram, what's the most common one? Vibram Edge rubber, the harder one. The harder rubbers, the harder climbing shoes give much greater wear than softer rubbers. I mean, by orders of 5-10 times in magnitude. So that's an important question for gym owners. You have a compromise of should I have hard wearing shoes or should I protect my holes? It's an important question to ask. So I made a machine where a piece of rubber turns around, and I have a specific sample, a set sample, which is autoclaved again, of course, to get the best surface. And I push this into the rubber, which is turning around. The sample is also turning, and I push it into the rubber with the force of a person, 80 kilograms. And I watch the wear. So this maybe should. Okay, this is it. It'll go up in a minute. The sample goes up with a force of 80 kilos. Now it seems quite extreme, and it is. This is a very soft polymer thing. You can see how much is removed. It's a huge amount. And you think, well, that's not real. Why do such a test? You don't have that sort of wear in a climbing centre. But if you made something that survives that, would it not be an idea? Here again, more commercially available polymer. You can see there the wear going down. And what we do is we hit this 130 times within an hour. It's important that the climbing hold has a bit of time to cool down again. That hit generates a lot of heat. And that's part of what we realized of the mechanism of wear is a huge amount of heat is generated, and you can see on the top there little tiny pieces of the hold. It comes with little tiny pieces, and these were once hot. And when they were hot, they were very soft, and when they're soft, they can easily come away from the resin. I just told you about dynamite, light, and now we present you with our solution. Same forces. This is dynamite. You can see there is still a bit of wear. Difficult to stop all these loose needles coming away. But at the end of the cycle, it almost slows down. The majority of the wear, by the way, is in the very, very first, the first hits. And these, I don't know if you can see it very well, but this is the result of the entire test, the 1 hour test. So why does Dynamond work? What makes it different? The main reason is its high temperature properties. So when the product is hot, it is still hard. These cameras flashing. In order to make hard-wearing polyurethane, you need, if you want pure polyurethane, by the way, you need to have your product hard when it's hot. How does it work? This one's for Lee. Actually, when you look on the atomic scale, it doesn't really say Dynamond on the molecules. But I thought I might just play with that. So, the key to having good high temperature hardness is putting all these MDI blocks together, getting as many of them together as you can, and not having cross-linking. And that's what we did. Dynamon's available in 8 colours at the moment, but last year our client sold just under $1 million in the USA, so we're going to be copying a lot of the American standard colours so that we can have a greater presence in the USA. So the top line is polyester resin and sand. There is wear on polyester and sand. It's slow, and it doesn't go fully polished. So we look on the y-axis here. That 0 would be completely polished, or dual texture holds, and 10 would be a cast hold directly out of the mould and how it feels. And you notice that they don't all start in the same place. That's because the softer holds, soft polyurethanes, feel softer. So you would argue that it's not the same grip in the beginning as well. What do we have here? So the majority of the polyurethanes, if you go to a systems house and ask for a polyurethane material, and you say you want it cheap, you want it hard, they will probably give you something like this bottom purple line here. Very easy to pour. One easy way of getting cheap fast gas resins is to liquid fill them and make them highly cost linked, and that makes it very, very easy to pour. Very controllable, but the friction properties on these materials are really, really shite. The next line up, the yellowy green one, this is Danolite, wears down very quickly relative in the beginning, but should give a mild texture, which is not 0. But yeah, if you're honest about it, it's quite close to 0. Above there is a very hard polyurethane, 510. This is still being sold today. Much slower wear, but goes to 0. Doesn't have capacity to have regenerative effects. The Dynamond, the green one, doesn't start, starts at the same place as a different one, but it keeps its texture for long. You can look at this timeline, maybe about a year. I'm putting labels on it. The blue graph, the bottom one, is our production capacity, and the turquoise one is our orders. Over the last year, we've had a more than doubling of orders, and only now have we managed to catch up with the pace. Not all orders are finished, but the pace at which we can get on top of it. You can see the difference in the hardness of it. The hold should be high quality. So what I decided is to start making a washer that's very hard, so it won't be damaged at all by the bolt over time. And that rigidity, again, can help polyester. But I'm guessing it's not as good as the dual bolt. Finally, down last, I talked about this before, just the schematic of what it is. So here we have the initial texture, and as the climate climbs on it, it wears down, and we find the sand. So the top one is the initial texture, which is quite good, and then as the texture wears down, it is its worst possible phase, and then the sand comes up, and the texture gets better.